Welcome to the longest video of your life. No, seriously, that's gonna be a long video, but it will have so much important information. And we will cover finally everything we learned till this moment about what graphs of functions can do. And you know, there's so many advantages of knowing this. There's so many applications in engineering, biology, medicine, and anything you can imagine. If you want to be a microbiologist, you need to know this. If you want to be a civil engineer, you need to know this. Aerospace, definitely. So grab your pencil, piece of paper, preferably 5, and let's do it. Graphing functions chapter usually summarizes everything we had before and whatever we learned about functions. But now it also reviews some material from the pre-calculus class. So to graph a function y equals f of x, let's start from identifying the domain or the interval of interest, basically the domain, or sometimes you are the one who decide where do you want this function to be defined. For example, if you have a long profit function from January to December, then you can decide to only check the profit from January to March, then you restricting the domain. So that's step 1. Step 2, find all the intercepts. That is handy because I want to know where my y-intercepts are and when my x-intercepts are. Y-intercepts can be found by setting x to be 0, and then x-intercepts can be found by setting y equal to 0 and solving it for x. So it's always the opposite one. That's what you should remember, the opposite. Now figure out the symmetry. If this function is symmetric, you better find this out. To know that the function is symmetric, you need to plug in a negative sign into your input. If a function basically swallowed the negative sign, you see it disappeared, f of negative x equals f of x, then this function is even. Just imagine y equals x squared, right? It is even, and the negative x squared is still x squared, and to be even means have a symmetry with respect to y-axis. It means when you fold it using y-axis, like a butterfly, the left side should match with the right side. If, on the other hand, the negative sign jump out like this, then this function is called odd. It still has a symmetry as well, but different kind of symmetry. You can imagine x cubed, the function that looks like a chair, remember? Now this one is symmetric, but with respect to the first and third quarter. If you fold these two, then, like a butterfly, it kind of should match if you flip it. Periodicity will be important, so you need to figure out if the function has a period. What is the periodic functions you know? Well, definitely cosine and sine x, right? Those ones are keep repeating and repeating and repeating, and that's why they're so good in representing sounds and waves. So to find the period of the function, plug x plus p, where p is a period. That's my period. If the function stays the same, even though you plugged x plus p everywhere you see x, then the function is periodic for the period p. For example, cosine of x equals cosine of x plus 2 pi, or 3 pi, or 4 pi, so on. That means it's periodic. Next, locate all asymptotes, horizontal asymptotes and vertical asymptotes. So to do that, we will do two things. For the horizontal asymptotes, those actually not that hard to find out. You just set the limit as x or t or any input you have goes to infinity for the function. If the answer is the number, let's call it L, equals L, then you found a horizontal asymptote, because basically it means the function at the infinity stuck at some kind of number, then like this. Then this number can be called horizontal asymptote. Function can cross horizontal asymptote as many times as it can, but at the end it approaches it slowly and never reaches it. Vertical asymptote, on the other hand, can be found where my function does not exist. F of x is not defined, does not exist. So basically look at the denominator. Look at the denominator. That's why usually D and E happens. And then you can check if the function has vertical asymptote there. You're supposed to check the limit as x approaches from the left and from the right, and then you might see the situations like a vertical asymptote. The function might go down from the left, up from the right, and this is the vertical asymptote. Basically the wall which you can never pass. So just a few simple, fast reminder from the beginning of the calculus 1 class. Now, then find the first and second derivatives and we will start using them. That's basically, I would even change the color to bright blue. This is the advanced calculus 1, middle of the calculus 1 class when we found how to find derivatives, first and second derivatives. And we're gonna need them to find extreme values. That's from the first derivative or second derivative test. Concavity comes from the second derivative, so first derivative, second derivative, points of inflection, second derivative, intervals on which f is increasing, decreasing, that's first derivative. And it's sometimes not practical to compute the second derivative, so some functions might need to be graphed without completing this step. Find critical points and possible points of inflections. But this step usually is done before. The critical points definitely come before this step if you want to find extreme values, right? But points of inflection can come later. So that means I want to find critical points. By the definitions are the points where the derivative is 0 or D and E. That's critical points, CPs. And then the second derivative 0 or D and E might show you inflection points as well. So if the concavity changed, then this point, if it's in the domain, is points of inflection, poi. If changed the concavity. Then find intervals on which the function is increasing, decreasing, decreasing. That's the second derivative. Concave down, concave up. That's the, increasing, decreasing, that's the first derivative. Concave up, concave down, second derivative. And we're gonna probably do these steps in once. These steps go together. Then we're gonna find extreme values and inflection points using first or second derivative test, and then finally graph everything. So I would say this part over here is the calculus part. In yellow is technically speaking pre-calculus part, but here in red is the calculus part. So that's the most important, what we learned. Well, I guess asymptotes, yes. Asymptotes actually show up in calculus class. Example. Sketch the curve y equals 2x squared all over x squared minus 1. And let's start doing this, following those steps. You don't have to follow the same order I just showed, but it's pretty intuitional after all. Yes, you can ask me, Julia, why we're doing all of this? We have graphing calculators and computers. It's 21st century after all. Well, don't you want to be smart and to know how computers doing that? That's exactly what they do. They actually find all those things I just listed. And there are many cases when computers are lying, unfortunately. So you have to be smart to analyze it yourself. Also, it's a very good summary of the whole material we just learned. Okay, let me do in blue color pre-calculus class stuff and then switch to calculus 1. So first, domain. We learned how to do domain long time ago. And domain will be especially important if there are points of discontinuity. Well, I definitely can see the denominator should not be 0, so x should not be plus or negative or positive or negative 1. That's my domain, so I can say that continuous from minus infinity to minus 1, from minus 1 to 1, and then from 1 to plus infinity. Which means these points are points of discontinuity. Points of discontinuity. Please remember what I'm going to say right now. When you find points of discontinuity for these types of problems, and you will keep going with first derivative test and second derivative test, always include these points. Note. Include points of discontinuity. Points of discontinuity means the function is not continuous there. So at this point I can see it's probably some kind of vertical asymptote here. Into sign lines. Because points of discontinuity might change the sign of the first derivative and second derivative. So you have to include them as well. I'll show you later. But basically put it in the box, it means we're gonna use it soon. Second step, let's find, what do we have second? X-intercept and Y-intercept. Okay, X-intercept, that means Y should be 0. When Y is 0, I'll put a double arrow, that means goes left and goes right. 2x squared all over, x squared minus 1 equals to 0. The fraction is 0. When the numerator is 0, then x is 0. That's my x-intercept. Y-intercept is even easier to find. Set x to be 0, and then if x is 0, then y is 0. So basically we have x and y, x, then we have 0. 0 as a point where x intercepts y and y intercepts x. That's what we found. Now the third one is, the third step says exploit symmetry. So let's figure out if our function is symmetric. To figure this out, I will plug negative x into my function and see what's gonna happen. If I plug negative x, I will have 2 minus x squared all over minus x squared minus 1. Look at that. Because we have squared everywhere the input happens, actually the negative sign disappears. The function swallows the negative sign. Then indeed, this is the original function over here. Negative sign did not change anything. Then we have symmetry. So it's symmetric about, well, first let's remember what it means. Which case is that, odd or even? If the swallow of the sign, it's like y equals x squared case. That's a parabola. Parabola is even. Even functions like parabola can be followed with respect to y-axis, like a butterfly. Then it's symmetric about y-axis. Now, everything we're going to plot on the left-hand side of y should be plotted on the right-hand side of y the same way. That was symmetry. Periodicity. If I plug x plus p, where p is period, into my function, it will be 2x plus p squared all over x plus p squared minus 1, and then you do square of the sum, and then you simplify everything, and it will not give you the original function. Are you kidding me? No way. So that means no period here. No period. That's good. Maybe not good, I'm not sure. Depends on the situation. Then asymptotes. Oh yes, let's review. I will change the color. The beginning of the calculus 1 class. Asymptotes. Vertical asymptote or horizontal asymptote? Which one do you want to go first? Vertical asymptote comes from the denominator. Look at the original function, for example, over here. And we already found those points. X squared minus 1 equals to 0. And it gives me 2 points, plus and minus 1. Those are 2 VAs. X equals plus and minus 1, vertical asymptotes. How about HAs? Horizontal asymptotes, to find them, no, that's VA. For horizontal asymptote, you need to set up the limit and basically check what's your function doing in the long run. Plus infinity and minus infinity. Let's see, 2x squared over x squared minus 1. 2x squared over x squared minus 1. Do you remember limits? I hope you do, because the answer is 2. How do I know? find the limit of the top, find the limit at the bottom, the leader. How the leader at the top, find the leader at the bottom, and then the answer will be the ratio of the leading coefficients. That's 2, because we have 2x squared at the top and x squared at the bottom. This is a number. That's the most important, that this is a number. Since this is a number, I can say that y equals 2 is my horizontal asymptote. You're also supposed to check the same limit on the left side, because it's not always the same. X goes to minus infinity, but since x squared swallows the negative sign, the answer is the same. But we definitely have examples of the function when it has two different horizontal asymptotes. One goes to, say, y equals 5, and the other one to y equals -5. So you have to check both ends separately. In our case, we have one horizontal asymptote, y equals 2, on both sides. So I will say both sides. Is my handwriting getting worse with more and more videos? Not sure. Maybe the coronavirus definitely changes the handwriting. Haha, bad joke. Okay, finally we start doing differentiation, and I will choose one more color. For example, purple. I like purple. So we're gonna do first and second derivatives. Yes, let's find the local maximum, minimum, increasing, decreasing, and then second derivative will show us concave up, concave down, and then inflection points. So the y equals 2 thick, 2x squared all over x squared minus 1. Then y prime equals, oh, it's not that simple. That's a quotient rule. So let's have more space. Do you guys remember quotient rule? You better do. X squared minus 1 squared denominator, derivative of the top 4x, copy the denominator, minus copy the top 2x squared, derivative of the bottom 2x. Simplify, and since we did it so many times before, I will just tell you the result, but you simplify by yourself. Minus 4x, x squared minus 1 squared. As you can see, the denominator did not change, it's just squared now. And the vertical asymptotes, or basically points of discontinuities, stay the same. That's pretty important to point out. And next time we're going to find second derivative, we will still going to have the same point of discontinuities, plus and minus 1. Well, I will put this in the box because the first derivative sign line will ask me to plug test points into that. Now I want to find where the top is 0 and the bottom is 0, because critical points, by the definition, are points in the domain, which makes your first derivative 0 and d and e. Why d and e are important? Because of the sharp corners. The sharp corner might be maximum as well, or minimum. Okay, let's solve it. So negative 4x, 0 when x is 0. X squared minus 1 squared is 0 when x is plus or minus 1. This is what I found. Now the question for you, are all of those are critical points or not? Critical points, by the definition I just said, are the points which are in a domain. These two guys here are not in the domain. We will include them on the sign line, but only x equals 0 is actually a critical point because it's in a domain. Now the sign line for the first derivative will show me where the original function is increasing, decreasing, and so on. Here's my first derivative, and I'm putting 0, which is my critical point, onto the first derivative sign line, but I also want to put -1, and I'll do it this way, look. Dash, 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 -1 and 1. And you'll be putting it everywhere. First derivative sign line, second derivative sign line. Because, I'm repeating it one more time, points of discontinuities might change the sign of the derivative, the first one and the second one. Okay, good. let's check. Choose some simple test points in those 4 intervals. We have 4 intervals now. What is on the left from -1? Well, say -2. Where do I plug it? Into the first derivative. That's why you code first sign line for the first derivative, and that's why I put the first derivative into the box. If I plug -2 into my first derivative, -2 times -4 becomes positive. Make a point, a very important point. The denominator is always positive. I will even point out. Denominator is always positive, and it's not 0, by the way. So it will never change the sign. After all, you just need to check only the numerator. Check only numerator. So thus, you should check only the top. -2 times -4 made it positive. Don't move. That's why I will put plus over here for the first derivative. Let's speed up a little bit. What happens if I plug 1? If I plug 1 into the first derivative, oh, I cannot plug 1. Sorry about that. I was like thinking, why should I plug 1? I need to plug something between -1 and 0. For example, -0.5. -0.5 times -4 is still positive. Now, when I start plugging positive numbers, -4 will make them negative. And since denominator is not changing the sign, it will be negative and negative from 0 to 1 and from 1 to infinity. You can check plug 1 million and you will see the derivative is negative. If the first derivative is negative, the original function, let's make it green color. The original function is increasing from -infinity to -1. Keep increasing after that till 0. Decreasing from 0 to 1 and then keep decreasing after that. Do you see this piece? That's my local maximum. So the first derivative test immediately told me where the local maximum is located. Let's make the summary. So the original function f, so the green color is about f. F is increasing from -infinity to -1. Do not include -1. Do you know why? Think for a second and I'll finish writing. Why we do not include -1 and 1, even though it seems like it would make sense to do that. So increasing from -infinity to -1, from -1 to 0, decreasing from 0 to 1, from 1 to plus infinity. Why would you include 1? If you include 1, you will have division by 0. At -1 and 1, your original function is neither increasing nor decreasing. It doesn't even exist there. Make sense? So you should not include these points. Now keep going. Next one is local minimum, local maximum. So that's the answer from the first derivative sign line. And one more answer is f has, look at the graph, local maximum at x equals 0. But also it's not very nice to just enter the input. Find f at 0 to have the output. Well, f at 0, that's the original function. Do you remember that? Plug into the original function to have the output. Why do we need that? To have a couple, x equals 0, y equals what? Well, the original function is 2 times 0 squared, 0 squared, minus 1, that's 0. And we know that at 0 the function is 0. We found x and y intercepts. So the local maximum happens at, let me do it here, at 0, 0. That's a good answer, because you want to know not only input but also output. In case this is the example of the profit function of your business, say you started a business, and you say that there's a maximum happening right at the day equals 0. You want to know how much money did you make, right? That's the whole point of finding the profit. Maximum profit was 0. Doesn't sound like a good example, but you got it. You know what I mean. Now, moving to the next step, which is finding second derivative. So still step 5, which is kind of annoying of the order we just listed. But we found already critical point and so on. I'll call step 6. Doesn't have to follow the order. Step 6. Let's find second derivative. Second derivative. I would say it this way to have an excuse. The list of steps I just gave you is a recommendation and you don't have to follow it. Yeah, that's very smart to say that. Now I don't have to follow it because I just realized I don't like it. But I don't want to change the video anymore. So the second derivative, f prime prime, is a derivative of the first derivative, which is negative 4x all over x squared minus 1 squared prime. And that's why you should be good at taking derivatives, because that will have a lot of applications from now on. Squaring the denominator, then differentiating the top will be negative 4, copying x squared minus 1 squared, the denominator, minus copying negative 4x. I decided to show you these things carefully because the chain we're gonna have one right now and I just want to review it. The derivative of the denominator is 2 goes down, copy x squared minus 1, change the power so it's to the first one, times derivative of the function inside, which is 2x. And then I will make a small note. That's chain rule. Your favorite thing ever, chain rule. Now keep going. Need to simplify this math, and you know I will play a genius card that in my mind I just immediately simplified into 12x squared plus 4 all over x squared minus 1 cubed to make the video a little bit shorter. Check that this is the case. I basically just used my own notes, okay? Put it in the box because we're going to be doing sign line for the second derivative and we will need to plug test points into this second derivative. Okay, let's find when the second derivative is 0. D and E points are not necessarily needed, but we're going to put them onto the sign line because those are points of discontinuity. Interesting, so to find where the second derivative is 0, as always, I need to check where the numerator is 0. Let's see what's gonna happen. 12x squared should be negative 4. Is it even possible? 12 is positive, x squared is positive, or 0. And then it will never be negative 4, so basically there's no solutions. That's fine. If there are no solutions, we're just gonna plug onto our sign line for second derivative. What should we plug there then if we did not find any zeros? We'll plug the zeros from the denominator, which are points of discontinuities. In some literature, they will tell you to find these actually. And then you can say that x equals plus or minus 1 will be the one from the denominator. But they are coming from the original function, even from the domain, remember? So technically speaking, you don't have to claim that they're coming from the second derivative. Nothing new basically happened. So those are the only 2 points I will plug onto my sign line for the second derivative. And now I need to check using test points on those 3 intervals. I'm going to plug test points in my second derivative. And if the second derivative is positive, then the original function is concave up. If the second derivative is negative, then concave down. If the point changed the concavity, it's inflection point, but only if the point is in the domain. Let's check. If I plug negative 10 into my second derivative, I want to point out now denominator actually might change the sign. Look at that. Since it's cubed, now I need to be careful. Denominator might change the sign, but the numerator is always positive. So now actually the numerator does not change the sign at all. I just need to check the bottom of the fraction. Let's hurry up a little bit. Negative 10, if I'm plugging to the second derivative, will be positive or negative. Negative 10 squared will be 100 minus 1 is positive, cube is positive, everything is positive. Putting plus. If I plug 0, why not? The test point can be 0 now because we don't use it as the critical point. At 0, I will have 4 over negative 1 cube. That's negative. And then I will plug plus 100. That will be positive. Then the original function f is concave up, looking like a smiley face, concave down, grumpy face, and smiley face again on these corresponding intervals. Now, what should you claim about negative 1 and 1? Are you yelling it's point of inflections? No, I just repeated so many times. They're not. I will point out again. Not poi because not in the domain. Now check with your textbook. Some of them might claim that it's fine to call them points of inflections, but most of the books agreed to call points of inflections only the points that change the concavity but also are in the domain. And those two are vertical asymptotes. So excuse me, they are not in a domain. We are almost done, I promise. Now we can finally list more information. More information are coming from the second derivative sine line. So I can say that original function f is concave up and concave down. It's concave up from negative infinity to negative 1, union from 1 to plus infinity. Concave down from negative 1 to 1. No points of inflections. No points of inflections. Also, we can now say, there's nothing else to say, we already found all maximum and minimums and so on. Technically speaking, that's the time for the very last step. The very last step says, let's graph it. Let's use all this information we just had, and I will call it step 7, and sketch the graph. 7, red color. Sketch the graph. Okay, we don't expect you to be super professional in this. I know many of you freak out when you're asked to sketch the graph, but I promise you, it's actually not that bad using the information we just had. You will see if I'm right or wrong. Here is my Cartesian coordinates sketch over here. And I will write down that I'm working with x as the input and f of x, or let's say y, let's say f of x, as the output. And I'm trying to graph the function I was given. If you don't remember the original function, I actually don't remember the original function. I'm talking about y equals 2x squared all over x squared minus 1. Now we're going through all the steps and carefully putting everything we learned about this graph on the coordinates. So the first thing I remember are those annoying negative 1 vertical asymptotes and 1 vertical asymptotes. They've been with us for a while, so let's put them here first. I also remember there was a horizontal asymptote. Do you know where? Go back and check. Pause the video and review your notes. The vertical asymptote was at 2. That's easy to check even right now. Check the limit of this function when x goes to infinity. It gives you 2, so you can figure out right away. That's horizontal asymptote 2. Vertical asymptote, vertical asymptote. Now, we also know that the function touches 0, 0, that's points of intercepts, symmetrical with respect to y-axis, so whatever we're going to plot on the left should match with whatever we're going to plot on the right from y-axis. We found that the function is increasing from negative infinity to infinity, from negative infinity to minus 1, and it's also concave up. So it's gonna go like this. If I have 2 asymptotes, I need somehow to make sure that the information matches. So you see it's increasing. I will even put the arrow up. Increasing and concave up matches the information we just found. It's still increasing after that and hits the local maximum. Local maximum is at x equals 0. Local maximum x equals, not x equals 0, but 0, 0 we found, input and output. So after negative 1 vertical asymptote, there is a break happening. Then it's keep increasing and hits the local maximum. Then it's decreasing, if you check increasing, decreasing information, up until it hits one more wall, which is vertical asymptote, like this. I will even make it more visual. It should be like this, super long, basically parabola concave down over here, from -1 to 1. Increasing, decreasing. And then it says it's decreasing again after 1. So it's going to repeat this shape. Now you can see it's indeed like a butterfly. If I fold it with respect to y-axis, everything should match. Also, it matches the idea that from -1 to 1, it is concave down. Here it is concave up on the sides and concave down after that. So we had all the information here actually. Everything we wanted is here. No periodicity, symmetry, and everything like that. So we also say that function is dNA here, so because of the vertical asymptote. The second derivative is positive. I will write down the first derivative is positive because it's increasing. The second derivative is positive, concave up. The first derivative is positive because increasing. Then the first derivative is negative because decreasing. But the second derivative is negative, concave down, grumpy face. Then the first derivative is negative, decreasing. The second derivative is positive, concave up. Very interesting. Congratulations! After this chapter, you officially can be called a professional in graphing all kind of functions without using computer or graphing calculators. And that's, a reason to be proud about. Because not everyone can do it, and actually that's pretty hard. And you should always assume that the calculator or graphing tool you're using might make a mistake. And soon you will learn some cases when the computer actually is lying. Sometimes due to the lack of memory and calculations, or sometimes it just doesn't know a good method to calculate everything. So it's important for you to be smart and to check your graphing tools by yourself. And I think it's just really satisfying that from now on, you can use all this knowledge we learned in Calculus 1 class to analyze the graph and to graph yourself. Thank you for watching.